electrode potential. Now, if a metal is dipped into a solution containing each metal, for example, if you say zinc, you drop zinc metal in zinc sulfate. So this zinc will dissolve to form a ion, and they will thus accept a lot of electrons to become negatively charged. Similarly, if copper is placed in copper sulfate, copper will lose electrons and will become positively charged. Now, this difference between a metal and its solution, the difference in their potential is called electrode potential. So I want us to write now. Let's write this. When a metal is placed in a solution containing its ions, when a metal is placed in a solution containing its ions, some ions of the metal pass into the solution to give this reaction. Metal become metal ion, aqueous plus electron. So pick whichever one. I have said here that metals ionize by electron loss. Look up. If I add zinc, this is a metal, it will lose electron. Zinc is zinc 2 plus, so it will lose 2 electrons to become zinc ion. That's how we get zinc ion. But because we don't normally write -2, we bring the -2 here, so it becomes zinc 2 plus 2 electrons. So this is, so whenever a metal is placed in a solution that is containing its ions, like zinc in zinc sulfate, this zinc will dissolve and form ion. It will accept electrons and the zinc will become negative. So this is how, when metals form ions, we call that ionization. Ionization is the process whereby a metal changes into an ion. This is a metal, but this is an ion. Metals ionize by electron loss, non-metals ionize by electron gain. Take note of that. But the question, what we want to see today is unique. Unique. If you look at this electron potential, you see that some metals have negative, some metals have positive. The significance of this you will see in the course of our teaching. Please write those equations first. Thus, if zinc rod is placed in a solution of zinc tetraoxide 6, thus, if zinc rod is placed in a solution of zinc tetraoxide 6, some zinc atoms, become zinc ions, Zn2+. Aqueous. Once it changes to ion, you put aqueous. Please take note. This like this zinc now. Here is going. This zinc solid. When it changes to ion, it becomes zinc aqueous. Some zinc atom become zinc ion, and the rod, that is zinc rod, becomes negatively charged. Negatively charged as a result of the accumulation of electrons. In a similar case, when a copper metal is placed in a solution of copper 2 tetraoxosulfate-6 solution, is placed in a solution of copper 2 tetraoxosulfate-6. Some copper is deposited on the rod, or the copper rod. Thus, copper loses electrons and become positively charged. This is copper Cu2 plus aqueous will accept electron to give you copper solid. Now, although they are metals, this should have been the right way to write ionization of metal. But in this case, zinc is having it this way, copper is having it this way. Opposite. Why? And that's why you want to look at electrode potential. You look at from this hydrogen downwards is positive, from the hydrogen upward is negative. So the hydrogen is a benchmark. So hydrogen is called the standard electrode potential. It's the reference point. It's hydrogen that is the reference point for us here. So this copper now acquires negative charge. Paragraph. Like that. Paragraph. So what can we deduce from this? The difference in potential between an element and a solution of its ions, element zinc and zinc sulfate, copper and copper sulfate, between an element and a solution of its ion is called its electrode potential on the line. It's called its electrode potential. So the difference between the potential of the ion, the metal, and solution of its ions is electrode potential. That's zinc and zinc sulfate. The difference in their potential. Copper and copper sulfate different. Electrode potential is a tendency of a metal to form a ion. That's all. So it's a tendency of a metal to form a ion. The electrode potential for a particular metal depends on one, the concentration of metal ions, and two, the temperature at which it is measured. Concentration of the metal ions and the temperature at which it is measured. What temperature? At what temperature do we measure this? Before we talk of our standard electrode potential, we must be talking about 298 Kelvin. In practice, the specified standard used for the measurements are the concentration 1.0 mole per dm cube and the temperature 298 Kelvin. If you subtract 273 from 298, so that let's convert it to degrees Celsius. This is 5, this is 2. So it is for 25 degrees Celsius. So I have given you the condition for electrode potential. 1. The concentration must be 1.0 mole per dm3. 2. The temperature must be 25 degrees Celsius or 298 Kelvin. Please take note of these facts. Because you see them in questions. Which of them is a condition? You see this in JAM questions, especially that of temperature, again and again. The potential difference, of course you know potential difference, your PD, volts. The potential difference obtained under these conditions is called standard electrode potential. The potential difference obtained under these conditions is called standard electrode potential. So let's look up. Let's see if we can define standard. This we know we will be talking about electrode potential, electrode potential, electrode potential. Now we are talking about standard electrode potential. If you look at it, when you talk of electrode potential, that's ordinary. But when you talk of the electrode potential, when the potential is 1 mole per dm, and when the temperature is 25 degrees Celsius or 270 and 8 Kelvin, that's standard. So what's electrode? Electrode potential is the potential difference of a metal or ion solution of ion. Electrode potential is the potential difference of ion solution or solution of an ion at 1 mole of concentration, 1 mole per dm cube, and at temperature of 298 Kelvin. Of concentration 1 mole per dm cube and at the temperature of 298 Kelvin. That's that. So the potential difference of any solution whose concentration is 1 mole per dm cube and at temperature 298 Kelvin is called standard electrode potential. Standard electrode potential for zinc. The standard electrode potential for zinc is minus 0.76, while that of copper is plus 0.34. I want to show you how we get the potential difference for your battery, your primary cell, your Daniel cell, electrical cell. You see the formula, and that's where we are going to, because to get the standard electrode potential for a cell, EO is the symbol for standard electrode potential. This is 0. So EO is equal to EO of cathode minus EO of anode. So if you look at EO of cathode, usually the ones lower, anything below hydrogen is usually used as cathode in any cell. You remember your cell, your simple cell, you usually have zinc rod and copper rod. The one below hydrogen, the negative, positive charge, are used as cathode. The ones above are used as anode. So when you look at it, cathode, if we have copper and zinc, which is just a simple cell, copper is 0.34 minus zinc is what? What's zinc? Minus 0.76. If you add this, give us plus 1.1. That is what you see on your battery, your Tiger battery. 1.1, whatever. So this is how we get the EMF, standard electrode or EMF of your cell. Take note of this thing I just said. So this is getting interesting, and I'm happy that we are getting to this point. The negative sign indicates that the metal, zinc, put in bracket zinc, has become a negative electrode, while the positive sign indicates that the metal, copper in this case, has become a positive electrode. You have something like this. If this is a cell, what is this? Is an electrolyte. You put a rod here, you put another rod here. This is zinc, the other one is copper. Now you connect them with what is called salt bridge. So this is copper, which is the cathode, and this is zinc, which is the anode. So the electrolyte for this is what? Zinc sulfate, and the electrolyte for this is what? Copper sulfate. This is salt bridge, and this is your galvanometer. Please draw that pic. Look up, please. If you look at this, remember what we have here. Now write this. The salt bridge in the half cell equation is represented by a double stroke. Please take note of this in case of any question in your exam. The salt bridge in the half cell equation is represented by a double stroke. Look at this. Look up. You see what goes on here? From zinc metal to zinc ion. So you write this one. Zinc S, one stroke, zinc 2 plus, ion A plus. Now because there are two now, there are two general. So you might have a double stroke like this. That they are linked. Then copper is what? Copper 2 plus, that's where it starts. I mean A plus. So copper solid. This is the equation, outside equation for this electrode potential. The single vertical line, between the zinc and zinc 2 plus and copper 2 plus represent the phase boundary. Represent the phase boundary, phase P-H-A-S-E, between the solid metal and its ions in solution. What I just said here is this. This single stroke is phase boundary that shows the transition from the zinc metal to the zinc ion. or copper AO to copper is just a bad phase. While the double stroke is what represents salt bridge. Salt bridge. So when you are done with this, you will now write the electrode potential by the corner EO equals 1.1 V. This is just how we represent this. So let's see a question. Let's look at the question. A question. Okay, given that Mg2 plus equals slash Mg solid EO equals minus 2.37 V. Mg2 plus equals slash Mg solid EO equals minus 2.7 what? 37 V. And Fe solid to Fe2 plus equals EO equals minus 1.44 V. It's still the same. Please take notes. 2 plus is 2 plus is solid. Find the EMF. Find the EMF. Or the electric potential of the reaction Mg plus Mgs plus Fe2 plus equals to give us Mg equals 2 plus Fe solid. So this is a question. So let's see how we derive the electrode potential. Electrode potential for this. The first thing we do is, if you look at the equation, oh, I didn't give it for this. What did I give for that? Minus 0.444 V minus. Now, if you look at this, this is going from Mg to Mg2 plus. If you remember, zinc to zinc2 plus. So for this first one is Mg solid plus 2 electron will give you Mg2 plus. That's the meaning of that. This one. We show this is what anode. Why this one gave us Fe2 plus aqueous to give us Fe solid plus 2 electron. So this shows this cathode. So now know which is cathode, and EO is going to give us what? E cathode minus E anode. Now we don't need to go to our table, because if they ask you, nobody expect you to memorize the table. They would have given you electrode potential for each. They give you for this from iron to what is from iron to metal, it is minus 2.37. But what we have, we don't have from iron to metal. We have from what? From metal to iron. This is from iron to metal. That's minus 0.44. So let's see what we now have. If we have to subtract, what will it give us? Which will change. I want us to look at it very well. Which will change? Because if you look at the two equations, they look alike. Look at it very well. Do you see that? This iron to metal. Do you see that? Now what? Iron to metal. Iron to metal. This is cathode. Go back. Cathode is cathode negative or positive? Go back to our table. I told you the ones lower are usually cathode. I mean, is cathode usually negative or positive? Positive. Therefore, it therefore shows that E cathode, this cathode, which is minus 0.44, will not be minus 0.44 this time now. Because we have discovered that it is what? Cathode. So it's going to be plus 0.44 minus. Why this one remains negative? Minus 2.37. What will this give us? 4 plus this 1, carry 1, 4 plus this 7 plus 1, 8. Then 2.81 volts. So that's our EMF for that cell. That's the EMF for that cell. 2.81 volts. Okay, that's what should be. Please look up. Please, let's look at this. Let's compare the equation to our own equation. This was what they gave us. Look at our own. Our own is going from what? Metal to iron. This was what they gave us. But in the real equation, it was metal to iron. It therefore shows that we reversed it. What they gave us, iron to metal. So we have metal to iron. It therefore shows that this electrode potential that they gave us minus is going to change to plus. It's going to change to plus 2.73. Because it's reversed. The real from the equation, when we compare it from the equation, it was reversed. It wasn't from this electrode potential given to us minus 2.37 V was for iron to metal. But when we look at the equation ourselves, what we derived there was from metal to iron. So it there was like it was reversed. So we just reverse the sign. That is positive. Why this one is from the equation given to us metal to iron to metal is still correct, metal to iron. So we leave the electrode potential that same way. So we still have it that way. Cathode.
Meaning the cathode will be minus.
Meaning the cathode will be minus 4.44 minus 4.44. Meaning the cathode is minus. This take note. So EO is going to give us E cathode minus E anode. In this case, the cathode is minus negative. That's minus 0.44 minus. If that be minus, that's what it can be. That's what it can be. Minus this, minus this. But we reverse it. So let's say plus. Because no more. Plus 2.73. What do we have? Minus 4.4 plus 2.73. This is 9. No? No? 13 minus 4 is 9. 6 minus 2. 1.29. Is it 2.29? Okay, you got 2.29, right? Minus 2.29b. Okay, that's what? Minus 2.29b. Okay, that's minus 2.29b. Okay, let's see this. Let's stop here. Minus 2.29b. Sorry, this is not 2.73, it's 2.37. So let's subtract that now. This is 3. 1.93. Okay, that's what we have. That's what we have. Can you notice something? Please look up. We can paraphrase or replace this thing from this. It therefore shows that after rewriting this equation, this one that was the anode, because it has changed to what? Positive side. We can now revise it as what? Cathode. So if we revise it as cathode, it's going to be cathode 2.37 minus anode. Now in this anode now, it's just going to be 0.44. But because it's going to cause confusion, we are not going to do that. So let's just leave it this way. So cathode minus anode, in this case cathode plus this minus. Still, it still doesn't matter. We don't need to change anything. If we had said this, watch me. If I also said cathode minus anode normally, the cathode was this. Is that not? Minus 0.44 minus anode. Anode is minus 2.37. The normal thing, I thought. So it's still going to give us minus 0.44 plus 2.37. The same. So not altering anything. Just leaving everything the way they were. Cathode minus. So once we are given a question, from the equation, just derive what is the cathode and what is the anode and apply the rule straight. Don't alter anything. Cathode minus anode, you get the answer. So this is minus 1.933. So we'll stop here and we'll continue from here next week.